Okay, so today we'll start with a completely different memory technology. The name says magnetic random access memory, or MRAM, magnetic RAM. Basically, RAM is going to be a type of memory that we'll talk about for the remainder of the semester. Random access memory. All of the memories that we'll talk about moving forward will probably be random access memory, right? And in front of RAM, there will be something added, M, R, P, whatever, and they will determine different technologies that we are using to make the RAM. So this is, as you can see, this is the first part of a magnetic RAM lecture. And I mean, before we begin, I just want to highlight that this is one of the most promising emerging memories out there. So we have covered two existing standard memory, including SRAM and DRAM, right? They're being sold for decades. They're well established. And, you know, they have been doing their job for a while, of course, but certainly moving forward, there are some challenges that these memories cannot overcome, especially with the amount of storage exponentially increasing. SRAMs are no longer favorable because obviously they need a lot of power to operate, and they are not non-volatile. So before we begin, I want to familiarize you with the term volatility and non-volatility. We talked about it before, but I want to reiterate. A memory, if a memory requires continuous power to remember what was supposed to be stored, then it's a volatile memory. The moment you remove power, the stored data is gone. SRAM is such a memory. DRAM, on the other hand, is in the middle. Like, yeah, at the moment you remove voltage, if it is like a really small, tiny fraction of time, much less than what it takes for the capacitor to fully discharge, then yeah, in theory, it's non-volatile, but practically speaking, it's not. It's essentially a volatile memory. You could only take the power off for a few microseconds maybe, right? As opposed to your flash drive that you could just take out of your computer and take it with you anywhere and then plug back in and your data is still there. So definitely there are some memories that are non-volatile. And the most important non-volatile memory that we currently use is flash memory, which we will talk about in one of the lectures. But this is a type of, moving forward, most of the memories, in fact, all of the memories that we'll talk about will be non-volatile. Okay, so magnetic random access memory is a type of non-volatile memory, meaning when you remove voltage or power and turn it back on again, it will remember what it was storing. So without further ado, let's start with a chart where you see the dynamics of different kind of memories and their performance. Let's see the write cycle time versus write endurance. This show you, you know, relative comparison between different kinds of memories that are emerging. SRAM, yes. Oh, I'm not sharing screen. Okay, thank you for pointing it out. Okay, thank you. Great. I hope I'm sharing screen on Zoom, just making sure. Yeah, looks like it's being shared, so. All right. Okay, so this is the chart that I was talking about. This is write cycle time. This is write endurance. What does cycle time means? Basically, how much time it takes to complete the write operation, okay? And how many times can you write? Meaning, can you write just 100 times? Can you write 1,000,000 times? Can you write 1,000,000,000 times? How many times can it take it, okay? Notice, SRAMs and DRAMs, they have almost practically infinite endurance. Basically, you could keep reading and writing them as many times as you want. 10 raised to 18 is insane. It's like literally out of the park, knocking it out of the park, okay? So no question about SRAM and DRAM endurance. And in terms of speed, they're also pretty good. Especially SRAM is the winner, clear winner. There is no other memory that comes close to SRAM, okay? So that's why we still use them, despite them being so energy hungry. Obviously, there are many other memories in the game, but I don't want to talk about them today. I want to talk about STT MRAM, spin transfer torque. Forget about STT, just look at MRAM, magnetic RAM. STT is a type of MRAM. There are many other kinds of MRAMs out there. We'll talk about several of them, and STT MRAM will be one of them. So magnetic RAM is definitely getting there. It's getting better. It's really fast compared to most other memories. And it has really high endurance compared to most other memories. You don't see all the memories out there. Obviously, I have to rely on different sources. This source only portrayed STT MRAM with respect to SRAM and DRAM, okay? So there you go. That's why I told you this is one of the most promising kind of emerging memories. Okay, all of these are emerging. They're basically up and coming, except for NAND and NOR flash. They're already there being sold. But notice they're not really that good in terms of performance when it comes to write time or even endurance. So the flash memories that we're using in today's computers, in your iPhones, they are not really as good as the STT-MRAMs if we could make them in bulk. All right, without further ado, let's start with the technical description there. The core component of a magnetic RAM is a magnetic tunnel junction. Okay, this is an interesting device. Notice, moving forward, starting from this technology, we'll rely on some fancy physical phenomena to store information rather than conventional charge like the SRAMs and DRAMs do. So this is the first kind of fancy device that we are observing together, okay? Let me explain what magnetic tunnel junction is. So in a simple fashion, it has three layers. It has a pinned layer, a free layer, and an oxide separating the two. What does the pin layer mean? Both of these layers are made of magnetic materials. For example, these are just examples, by the way. You don't have to necessarily use only this material. Okay, this is more like an alloy. Let me use a different color here. This is an alloy, cobalt iron alloy. It's a magnetic material. Iron is a magnet, as you know. Iron is a magnetic material, but there are many other kinds of magnetic alloys that are out there. Instead of conventional elemental magnets, we use different alloys of magnets. And there are reasons. Obviously, we couldn't just jump into this material and started using it, right? There were years of material science research that went in and tried to figure out and narrow down the materials that would be beneficial for this purpose. And we'll get into the specifics later on, but let's start with this very basic understanding that these two layers will be magnetic materials. So they could be magnetized. They could be magnetized in one direction to point to one direction or the other. For example, this arrow represents the magnetization direction for the domains inside this material. You guys all know magnets. You know that we could always make the magnetic domains point to one direction or the other, north or south, however you want to put it, right? So apparently, in a magnetic material, you could always somehow electrically program them into one direction or the other. Now, this layer, this oxide layer, separates the two magnetic layers. Okay, it doesn't need to be just magnesium oxide. There could be other oxides as well. And I have a slide specifically that talks about why magnesium oxide is our choice. This is basically the best oxide that we could use for magnetic tunnel junction as of now. Okay, so the simplified picture tells you how simple, like it shows you how simple the device is. But in part 2 of this magnetic tunnel junction or MRAM lecture, I'll show you how complicated this device can actually be. Instead of just one magnetic layer, nowadays people have to use many. So in fact, there are magnetic tunnel junctions with 10 to 12 layers. Okay, and here is what they mean. So there will be multiple sub layers within the pin layer and multiple sub layers within the free layer. And then oxide is just oxide. There will be no other layers within oxide, okay? So oxide is typically steel magnesium oxide. Free layer will have multiple sub-layers, but collectively we call them free layer. And pin layer will have multiple sub-layers, but collectively we call them pin layer. For most of the discussion, we'll be looking at 3 layers: pin layer, free layer, and oxide. And towards the end of the discussion about MRAM, I will show you how it realistically looks like. And that will also be the reason why it's so difficult to make. Because if you have 12 layers of materials to make one device, and you need others, by the way, it makes it challenging and expensive to fabricate. So that's the challenge. Okay, so why do we need these 2 magnetic layers, and what are we trying to achieve with it? Okay, turns out you can, by the way, you can select the magnetization of these 2 layers to be facing in the same direction like this. This configuration is called parallel or PMTJ, parallel magnetic tunnel junction. So parallel oriented magnetic tunnel junction, okay? On the other hand, you could always make them face in the opposite direction, exactly opposite direction. That's anti-parallel, AP. So AP MTJ or PMTJ. Interestingly, people realized, and this was discovered, there was a paper in Science, like one of the top journals in the world, where they reported, hey, we discovered magnetoresistance. What is magnetoresistance? So this is essentially magnetic, everything is magnetic as of now. We haven't talked about electricity yet. Turns out when you apply a voltage across it and try to flow a current through it, the current experiences different levels of resistance flowing through the same. You didn't change anything else apart from the magnetic orientation. But because of different magnetic orientation, this configuration shows low resistance and this configuration shows high resistance. Am I making sense? This is an observation. I haven't explained why, right? Just an observation. And remember, magnetization is not supposed to be related to resistance, right? Resistance is a very different property. But turns out, because of the relative magnetization of these two orientation, you have two different resistance levels coming out of the same device. Well, the first idea that should come to your mind is, hey, hold on a second. Can we then use one of this configuration to represent 1 and the other one to represent 0 and make it a memory? You see the point? So obviously, there are many other usage of magnetic RAMs and spintronics in general. I haven't used the term yet. I'm going to use it in the next slide, spintronics. There are many other uses, but one of the possible use would be this, to make memories. Okay? So let's see how you can. First of all, there are two things when it comes to deciding whether a device could be useful as a memory. First, can you have two physically stable states that you could, represent 1 and 0 with? Yes, check. Number 2, can you at will program these two states whenever you want? Like, can I go from here to there and there to here? Can I program 1 to 0 and 0 to 1? That's the other question. Because if you cannot, then it's not a memory device. Okay, so you have to see whether and how can we electrically change this. And oftentimes people talk about not using electricity to change the states. That becomes tricky. But if you are trying to use it with, say, a processor, the processor needs electricity and operates with electricity. So when it communicates with the memory, it should be able to program the memory with electrical signal. But if the memory requires magnetic signal to be programmed, and by the way, this type of memory that required magnetic signal, magnetic pulse, or magnetic field to program existed decades ago. Okay, like they're very old memories, magnetic disk memory. Basically, you needed external magnetic field to change the polarity from north to south, south to north, something like that. We're not talking about those type of magnetic memory. Okay, this is a magnetic memory that could be changed or programmed using electrical current. That's the interesting thing here. But how can we change the magnetic orientation using electrical current? Have you thought about it? Notice when we were in high school or even primary school, we must have played with magnets, and there are experiments that we did, right? How can you change the direction of a magnet with another magnet? Because the magnetic field interacts with the magnet. So you needed magnetic field. Remember, what I'm asking you is to not use magnetic field, but to use a simple current flowing through the material and use it to change the polarity, change the direction of the magnet. That's why it's unique. Okay, and I'll show you in a second with an animation as to how it works. Okay, before I say so, let me clear this up. Imagine you are flowing electrical current in this direction. I'm looking at anti-parallel to parallel switching. This is anti-parallel, is it not? Because they're pointing in the other direction. Okay, anti-parallel to parallel switching. Okay, before I show you the animation, I want to tell you one thing. How many of you have heard about electron spin? Okay, some of you, that's okay. That's why I asked the question. So in fact, this kind of memory uses the concept of spintronics, manipulating electron spin with electronics. That's called spintronics. Okay, and what is electron spin? If I ask you, what is the charge of an electron? Would you be surprised? Oh yeah, does electrons have charge? Yeah, they do. Protons, yeah, they do. You'd never be surprised because yeah, it's supposed to have a charge. Electron needs to have a charge, sure. But if I tell you, hey, do you think electron has a spin? Basically, charge and spin, they're both fundamental properties of electrons and other particles. It's not, anything uncommon. But turns out charge is a property that we most often talk about and use, that we are all used to using charge. Or we are all used to the fact that electrons have charge. Similarly, there is a fundamental property that electrons possess, which is spin. It's not what the name suggests. Electrons I want to clarify, electrons don't really spin. Oftentimes we use this type of analogy that, hey, imagine some electrons are rotating clockwise, that's plus of spin. Some electrons are rotating anti-clockwise, that's minus of spin, which is wrong, okay? Okay, I cannot go into the exact detail and the detailed description of what spins are, or, spin property means in general. So before coming to the class, I uploaded 3 interesting videos, which I personally liked. 2 from PBS, 1 from another YouTube channel that really nicely explains complex concept with funny videos, like 5-10 minutes. I don't want to make it a hour-long lecture because I'm sure then you'll not listen to it. But if you're interested to know more about what spin is and why is it not the same as spinning particles, watch those videos, okay? And if you have questions, you can ask me. But for the sake of this course, we're just gonna assume that you understand what spin is. Electron has a property called spin, and electrons can have 2 types of spin, plus of and minus of. If just imagine, like, if I told you electrons could have 2 types of charges, they don't. They just have 1 type of charge, for example. It's similar to that. It is a property, but electrons can have plus half or minus half type spin. Now, if you have 10 electrons in a system, chances are 5 of them will have plus half, 5 of them will have minus half. So half of them will have 1 type of spin, the other half will have the other type of spin. There is not always necessary, but it's about that type. Okay? Making sense? I mean, we cannot count electrons in 10s or 20s, as you can imagine, right? A humongous amount of electrons. But in general, in a quantum system, if a system is full, typically you always have plus half and minus half electron at every state, every quantum shell. So that's the reason I say it's almost half and half. If there are quantum states where you have unfilled position, meaning just 1 electron, then you can have an asymmetry in plus half and minus half distribution. Okay, don't worry too much about the stuff that I just said. Just remember, electron could have plus half and minus half spin. Now, this animation shows you 2 types of electrons. Can you notice that on your top left? The yellow ones, imagine they are plus half. The green ones are minus half. And typically we represent them with different kinds of arrows because they behave differently. When electrons flow through a wire, you don't see any difference in electrical current. But when you use magnetic field, that's when these electrons start behaving in a different way. Making sense? So anything magnetic, that's when you see the difference. Okay. So imagine when you flow electrical current in this direction. You guys all know this. According to convention, electrons flow in the other direction, right? We chose the electron current direction to be the opposite of the direction of electron flow. You might remember that. Okay, so electrons will flow from here to there. Okay, as the animation will show you. By the way, this animation will go by fast, so you have to all pay attention to it together. Okay, I will play it a couple of times to make sure you can all see it. Are you ready? I'm gonna first observe what happens, then I'll explain why it happened. So electrons are flowing. Notice, okay, something changed. I told you the animations will go by fast, but let me explain now. Notice between the 2 types of electrons, only 1 kind flew past the pin layer. This is the pin layer. Now is the time I explain why these 2 layers are given 2 different names. Why not layer 1 and layer 2? Why we call them pin layer and flea layer? Because one of the layers have stronger magnetization, and that's why it's very difficult to flip its magnetization. And the other layer has weaker magnetization. This is by design, by the way. We choose it to be like that. So it can be flipped. So the free layer, FL, oftentimes represented as FL, free layer, could be flipped. Its magnetization is weaker. Okay, but the pin layer is very strong. It's very difficult to flip it. Okay, so now when you had 2 types of electrons with 2 different kinds of spins, the ones that had parallel spin. So let me show you. You see that these yellow ones had similar direction in terms of magnetization. Making sense? So basically, just to represent that one kind of electrons will have preference over the other. Okay, so one kind, either plus half or minus half, will have preference to flow through this magnetic material. So it's kind of like a filter. It will filter out the 2 spins. One of the spins will be stuck and they cannot go through. The other one will go through. And by the way, remember, we are using a classical analogy here. The practically, like I said, it's not really electron spinning or anything else. It's a property that electrons possess. And there are spin electrical states, quantum states that the electrons spin in. If I try to get deeper into it, every material has some quantum states, and depending on its magnetization, one kind of electron could be accommodated, the other kind may not be accommodated. Okay, so there are no quantum states for the electrons to fill in when it tries to get into the material. That's why it doesn't get in. But in a very simplistic way, to remember that, again, it's not the real explanation, it's a way to remember. If there are electrons that are pointing in the same direction as the layer, they will be able to pass through, and the other one will not. And I'm happy to share a resource that will talk about the real reason with quantum mechanical band diagram, which again is a little bit more advanced. So if you are interested to know about it, let me know. Okay, all right. So one kind of electrons will pass through, the other one will be stuck, and that's what you saw here. But let's see what the ones that were passed through, what are they doing here? Can you see that? Let me try to go back again and show you one more time. So they're here, and they're interfering with the free layer and flipping the free layer and then passing out, like going out. Am I making sense? Why? So that's where the term STT comes in, spin transfer torque. Okay, imagine you have something like that, like a mechanical wheel kind of thing. Okay, so when you put pressure here, when you try to apply some force here, it basically creates a torque. So it rotates the material and it flips it, does it not? So similar to that, electrons can exert a kind of torque on the magnetic domains of this material. And because of that torque, when the electrons transfer their torque to the material, it basically flips the material. Am I making sense? Let me go back and show you again. So these electrons that were able to pass through the pin layer, they got stuck in the free layer for a while. Why did they get stuck, by the way? Can you imagine why did they get stuck? Because notice, they have the opposite magnetization and they were stuck for a while, but the free layer is weak. It couldn't just, hold on to the electrons. So electrons instead, since there are many electrons, their collective, spin torque eventually was transferred to the material itself, and the material flipped its magnetization and have apparently become parallel. So this is an anti-parallel to parallel switching. Does that make any sense to you guys? Does it? Okay, so that's how you do anti-parallel to parallel switching. But now, as a circuit designer, when you look at from a higher level, you just flow current and the current flips the material. You don't necessarily need to get into the detail of why it does what it does, but you can. There are physicists who are looking at it, material scientists who are exploring this, but as an engineer, you could choose to just use the current and flip it and not worry about it, right? It's your choice. One other thing, what you need to be mindful of. Okay, I will explain that after explaining the second switching, and then I will talk about it together. Only then it will make sense. So let's see. For the other kind of switching, this is parallel to anti-parallel switching. Parallel to anti-parallel. Okay, so this was parallel to begin with. Notice. Now I'm going to flip it to something opposite. And remember, I can never flip the pin layer. I'll have to flip the free layer all the time. So let's start there. So again, I will accumulate electrons here. Notice I'm flowing current in the other direction, opposite direction. And now when current flows in this direction, electrons will get to the other direction, as you can imagine, right? Now, see, the electrons that were pointing to the same direction as the free layer, they passed through, and the other ones got stuck for a while, but then they exerted torque on the free layer and then passed through again. The process is essentially same, but the difference is, for one case, you are letting current flow from the pin layer to free layer, and for the second option, you're letting current flow from free layer to pin layer. And this is a necessity. You cannot just flow current from one direction and, okay, let's see. Imagine you are flowing current from, I have to go back to the previous slide and restart the animation, only then you'll be able to see. Remember, for this one, tell me something. So you had up and down electrons, and only this one's passed through. Should use a different color here. and interacted with the spin and flipped it, right? As you might remember. What if I passed current from the other direction? What if I passed current from the other direction? What would have happened? Can anybody guess? So this one will pass through. Okay, this one will pass through quite easily and will interact with. So basically, when they get to this side, notice when they get to, I'm struggling with color. Let me use this color instead. So this ones, just notice as I pointed out, these two will pass through easily from the free layer. But when they get to the pin layer, that will be a challenge for them, right? Because it's opposite. So this layer will basically not let them pass through. Okay? Versus the other two will face some issues getting into the free layer itself. Okay, getting the free layer itself. But then they will try to flip this free layer. And then when they flip the free layer, notice this. This is where the challenge is. When they flip the free layer to this direction, these electrons will also flip. You see that? And then they cannot pass through. So all of the electrons will be stuck. Here, none of them will be able to pass through. So apparently, the electrons only go when they decide that there is a clear way for me to pass through the entire stack. So they know none of the electrons will be able to go through eventually in this layer. All of them will be stuck. So apparently nothing will work. Am I making sense? That only the electrons leave this layer, then they exert a torque and they flip the layer. But if they cannot leave the layer, there will not be any flipping. So that's why to flip anti-parallel to parallel, you need to pass current from the pin layer to the free layer. And for the opposite, parallel to anti-parallel, you need to pass current. Am I making sense, folks? Yes. So let me show you. So there are some other reasons. Let me show you. Say this is, so typically, oh, sorry, I meant to just point out one of them. Okay, so for this kind of a situation where you are passing electrons from the top layer, from the free layer, okay? Let's see. These two or these types of electrons will be able to pass through easily from this layer. And then notice, they will not exert any torque because they are parallel. So they will pass through quite easily. Any problem so far? But then what happens to these electrons? Let me use different color here. They're stuck. But you need these electrons to eventually flip this guy. But they will never be let in by the pin layer. See that? Yeah. So notice, it's not the current flow which flips it. It's which kind of electrons flow. Let me rephrase that again. So let's talk about, instead of plus up and minus up, let's talk about top or up spin, down spin. Can I use that term? Up spin, down spin. And by the way, this is a textbook term. Many textbooks will use up spin and down spin instead of plus up and minus up. Plus up and minus up come from quantum mechanical calculation. But for the most practical discussion, we use up spin and down spin. Okay, let's do that. So apparently this is pointing up and this is up spin and down spin. So to flip this magnet, which spin do you need? You need down spin. Okay, so let's see. Let's try to point out these two electrons or these types of electrons. There are not two, like millions and billions. These electrons will easily flow through this layer and eventually the next layer because they are both pointing up. But then the other electrons will never be able to pass through the pin layer, apparently. So then if they could pass through the pin layer, only then we would have let them get to the free layer and then interact with them and eventually flip. But they're not. Or, yes, electrons are passing through, but the electrons that are passing through, they have the same up spin as the magnetic direction of the layer. So they will not do any type of torque interaction. Making sense? Did I answer your question or no? Yes. Sorry, could you? Yes, yes, yes. So this is what we are looking for. Parallel to anti-parallel and anti-parallel to parallel switching. So I'm talking about how you program it. Yes, if we had these two structures, we would have represented them to 1 and 0 and had a storage. That's fine. But can we selectively program them using electrical current? That was the question. And yes, looks like we can, but we have to be mindful of the direction of current. Okay, you cannot memorize this, but I mean, to some extent, you will get it used to it. Remember. So when you try to, let me just go back to this slide. Okay, when you try to flip anti-parallel to parallel, let's summarize this. You flow current from the free layer to pin layer. Maybe you can keep a note somewhere, right? But this is basically universal. And when you flip parallel to anti-parallel, you flow current from pin layer towards free layer. So this is a big ask, by the way. You need to change the direction of current during write operation. No other kind of, we'll get to it. And I don't want to get ahead of myself. Just keep that in mind. You need two different directions of current. Okay. So moving to the next one. There are two kinds of magnetic tunnel junction, and these are super simplified diagrams for you to get the hold of the idea first, and then we'll get into the more complicated diagrams. One, this is called perpendicular magnetic anisotropy, MTJ, or PMA-MTJ, perpendicular magnetic anisotropy. So basically, the magnetization direction will be like perpendicular to each other. This is how they point. But as you can imagine, the other one is horizontal or in plane. So typically we mention them as in plane, as they are parallel to the plane that they are in. Okay, so there are some other magnetic tunnel junctions that are in plane, and both have pros and cons, by the way. And these all come from material level exploration. People tried with different combinations, different magnetization, different material, different thickness, different shapes. For example, for perpendicular magnetic anisotropy, PMA-MTJ, these magnetic tunnel junctions are always circular in cross section, unlike the one that you're looking at right here. Am I making sense? This is a cartoon, but practically they're always circular. Okay, but in plane magnetization, it's typically elliptical shape. Can you imagine, like, somebody will know it to begin with that this in plane will only work if you have elliptical shape? No, they tried with different combinations. They studied it with theory and experiments, and eventually they arrived at a conclusion that, oh, this will work best if you have elliptical cross section, not circular, not square or anything else. And this one will work best if you have square cross section. By the way, you guys have options to ask me questions. For example, if you ask me why, I could tell you, but if you don't, then I'm tempted to go to the next slide. Okay. And maybe for this one, I'll explain anyways. Look at the term anisotropy. Okay. Anisotropy represents an asymmetry, basically. So magnetic materials have a preferred axis. If you give it a chance, maybe if you let me just go back here. Imagine you have a preferred axis. This is your ECE axis. And that comes from the crystal structure of the material. Okay, that crystal structure determines that in one direction, it will be more energetically stable. Now, if you somehow magnetize it in a different direction, sure, it will stay there for a while, but then it will, if you give it enough time to relax, it will gradually go down to the ECE axis. Am I making sense, folks? Okay, so imagine you have magnetic tunnel junction like this, and you somehow make them parallel, but its ECE axis was this. Imagine what will happen. At some point, if you give it enough time, this will gradually relax and get back to the ECE axis. And it's no longer parallel or anti-parallel. You don't know what it is storing. Did I make any sense, folks? So in a magnetic tunnel junction, this is oxide. Imagine you start here, parallel or anti-parallel, but because of the ECE axis being in a different direction, it gradually relaxes down this. You don't want that to happen. Okay, so what I'm saying is the shape has a role in determining the anisotropy. Okay, how much energy it will have and how much interest it will have to go back to its ECE axis, and how soon. how aggressively will it go back to the z-axis. So that is related to the geometry as well. If you make it square versus circular versus elliptical, that determines the amount of anisotropy that you can generate. Making sense? That's why, and with some research, people figured out if you make PMA MTJ circular in cross section, they give you the more stability. Can anybody guess what is this relate to? There is a property that I talked about. Yes. That's true. But what I'm asking is, what type of memory parameter or property is it relating to? So, for example, is it related to retention? Is it related to endurance? Is it related to power? Basically, I gave you the answer, the first option, retention, right? So how much or how long can it hold on to the data? If it takes a millisecond to always go back to easy axis, then its retention is a millisecond. But I told you it has a really high retention. That means the process to go back automatically, yes. That's a great question. That's a great question. There are many, for example, it's easier said than done. We would have loved to design it in a way that it will always be in the easy axis. But remember, first of all, have you guys heard about the crystal plane 100,111? If you have taken 335, you must have gone through this. But so there are different properties that the material provide along different planes. And we are after a specific type of property. For many semiconducting material, we go after 100 plane. Okay. For other devices, we go for 110 plane. So in one of these planes, you have the more favorable electrical properties. And I haven't even started telling what those properties are. But magnetoresistance, for example, magnetoresistance is one property that we're looking for. In one of the planes, you have favorable property, but the other plane has the easy axis. Now, if you go for the easy axis to begin with, you help with retention, but then you struggle with magnetoresistance. So there is no free lunch anywhere. It's a great question, by the way. But did I answer your question? Okay. So apparently, people figured out better ways, by the way. It's not that much of a headache that we have to always go and make the easy axis being the axis that we use. Using shape anisotropy, meaning using appropriate shape, circular, elliptical, they could enhance the retention to billions of cycles. So like a long time, apparently, like years, and endurance to billions of cycles. Making sense? So that's how people arrived at this conclusion that, hey, you need to use circular for PMA and elliptical for in-plane. Okay, and there are other usage for in-plane magnets, which I will get back to in the next part, like part 2 of MTJs, not part 1. Okay, so we're heading into array level, as you can imagine. So we start with, why did I take so much time talking about this device? Because I'm almost sure none of you have ever encountered this device in any courses. Have you? Isn't that the first time you're looking at magnetic tunnel junctions? Or no? Okay, that's the reason why I wanted to talk about it to some degree of detail. And this is a fundamental device that is used in most spintronic applications. And spintronic application will go beyond memories. There are many other applications that is necessary. Okay, so now getting back to the memory side again. Same old story. For memory, we need to have one cell that will store information. And we have to be able to control that cell at will. Okay, so to achieve that, this is the easiest possible structure of a memory cell with a magnetic tunnel junction. Magnetic tunnel junction by itself is not the memory. It needs a controller. It needs a selector. Okay, the transistor here, as you see, it acts like a selector. I guess with me so far. So this transistor helps us determine when to write, when to read. Okay, so you need one transistor and one MTJ to create a magnetic RAM of the simplest type. And this magnetic RAM is called STT-MRAM, spin transfer torque magnetic RAM, or STT-MRAM. And that's what you saw in the chart that I first showed you. Okay, this is the most popular version of magnetic RAM. And there are other more complicated versions. Okay, and I already explained this magnetic tunnel junction, when they have parallel state, they have low resistance state. Get used to this term, LRS and HRS. We'll be using it quite often. LRS represents low resistance state. HRS represents high resistance state. Okay. All right. Now, take a look at this 3D image again, which shows how things are connected. This is how the transistor looks like. Can you guys see that as I draw? This entire thing is the transistor. And this is the drain, this is the source, this is the gate, as you can see. The reason why it looks so strange is because it's a FinFET. You probably haven't seen FinFET layouts before, I guess, unless you have taken 433 with me. But yeah, otherwise, I mean, typically when I teach 433, I try to cover FinFET layout in a couple of lectures. Not couple of lectures, couple of slides actually, because we didn't have the PDK for FinFET layout before. So you had to do bulk layout anyways. But this is how the FinFET really looks like. But regardless, just set that aside. If this is a transistor, on top of the drain terminal, you attach the magnetic tunnel junction. Is it not similar to the DRAM structure to some extent? You had a transistor, on top of it, you had a capacitor. Remember? Kind of like a drum. The difference here is magnetic tunnel junction are tiny, like really, really small. They don't need to be large to store more charge. They're really tiny, nanoscale, 10 nanometer to 20 nanometer diameter, if you think about it. This is like insanely small, okay? And this is a realistic picture, as you can see. A top view, imagine, if you're looking at it from the top view, this is how the transistor looks like. This is the word line. Word line is connected to the gate of the transistor, as you can remember. Correlate these three diagrams together, okay? Pay attention. Word line is connected to the gate of the transistor. See, word line connected to the gate of the transistor. Notice, this is the gate of the transistor. Do they all correspond to each other? Okay. Bit line and source line. Okay. Let's talk about source line first. Source line is connected to the source of the transistor. This is source line, SL. So notice, this is your source line. It's connected to the source of the transistor. How do I know it's connected to the source? Can you see this yellowish zone? This is a metal line. And notice this square-shaped object, black object, that's a contact. So this source line is connected to what? This is source, this is drain. So source line is connected to what? The source of the transistor. That's how we know. Despite it going over the drain, it wasn't connected. It's an upper metal layer. It's only connected to the contact. Okay, so that's where it is connected. Okay, what is this? This is bit line. Bit line is connected to basically on top of the magnetic tunnel junction. So that's why you see this dashed line represents the magnetic tunnel junction. On top of it, there is a bit line. So this is how it looks like from the top view. Okay. Are you guys all with me so far? Can you notice one thing? That the magnetic tunnel junction falls within the footprint of the transistor layout. Is that a good thing or not? I had a discussion about it during the DRAM lecture. Remember 6F square versus 4F square? At some point, DRAMs used to need, like to make capacitor, we used to need more area than the transistor itself. So then it was 6F square, 8F square. But now we managed to keep the capacitor within the transistor. And for magnetic tunnel junction, don't you have the exact same advantage? It's within the transistor layout. So you're not creating any offset. So what will be the layout footprint of MTJs? 4F square, which is dictated by the transistor. We talked about 2F and 2F being the minimum dimension achievable. So you have the minimum possible area density. Who is the culprit in terms of area? If I try to make the MRAMs even smaller, like make it 5 nanometer, will it help in terms of reducing the cell size? Can anybody tell me? Will it? You're right. But can anybody else guess why wouldn't it make a difference? Because the transistor is the bottleneck, right? If it is already smaller than the transistor area and it's already within the transistor area, if you make it small, it's not going to make any difference in terms of the overall cell area. Who determines the overall cell area? The transistor. If you make the transistor smaller, then you win. And I'm getting ahead of myself, but there will be a slide towards the end of this lecture where I will show you that there is a memory technology where we use magnetic tunnel junction, but we completely get rid of the transistor underneath. Like completely get rid of it. And that gives you a humongous advantage in terms of area, like unbelievable density. And that is the best case scenario as of now that we know of. Okay. And that's where we are headed eventually. Okay. So keeping that in mind, are you guys all with me so far, or have you given up? Like, okay, I save. Don't give up. Okay. If it is difficult, if it is boring, let me know. I'll try to teach it in a different way. All good? Okay. We have 4 minutes. In 4 minutes, I can finish this slide at least. If you pay attention. Okay. Let's see. Ready to hear it? How do you read? How do you write? This is a general slide that we use for all memories. And this is probably the most important slide for you to know. Even if you don't understand how spins work, blah, 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 you should understand how read and write works in STT-MRAM. Okay. Okay. Let's see. First, start with read operation. This is the STT-MRAM structure. This is the other structure. Can you tell me the difference between these two structures quickly? Yes, the magnetic tunnel junctions are two different kinds. I'm going to show you what you sense. You cannot sense and see where they're pointing. It's not possible for us to see. We sense them electrically. Did I tell you that one of the MTJ has higher resistance than the other? So you apply a voltage. There are two approaches to read it. Let me show you. Just forget about this complicated stuff. Apply a voltage, say Vx. If you apply a voltage, the same voltage to both of them. In one of them, you'll have more current than the other. Why? For the same voltage, when you have low resistance, the current will be more. V equals IR. Can you imagine that? Okay. So, and then you have a sense amplifier that senses whether the current is high or low. So there has to be a reference. So if you have a reference current and you see the cell current, if your cell current is higher than the reference, that means it has a parallel MTJ, so low resistance. If your cell current is high, making sense at all? Okay. So that's one option, to apply a voltage, constant voltage, and sense the read current. The other option would be to apply a constant current and sense the voltage. Typically, we prefer the first option. Apply a voltage, it's easy to apply a constant voltage than to apply a constant current. Okay. So we apply constant voltage or read voltage and sense the current difference. We'll see the array level picture, don't worry, in a second. But that's the fundamental way. Notice, read operation is unidirectional. What do I mean by that? Meaning you apply a voltage and the current flows in one direction. One direction. How do you write? We just talked about what you need to do for flipping a magnetic tunnel junction. You need to provide current in one direction or the other. So you need bidirectional current flow. Is it true? I guess with me? Okay. So to flip this parallel to anti-parallel, we need to flow current in this direction. To flip this anti-parallel to parallel, we need to flow current in the opposite direction. So what do we need to do? We need to flip the polarity of these two lines. So this bit line and source line. This is bit line, this is source line. We need to flip the applied voltage. Plus minus or minus plus. You see that? Which is a difficult thing to do, by the way. It's not easy. Flipping polarity is not an easy thing to do. There are one other kind of memory where we change the polarity of the current, but we didn't have to flip anything. Let me show you. That's our DRAM. Remember, bit line, when you write, you apply VDD to the bit line. And then when this was storing 0, it charges the node and takes it out to VDD. When you try to write, you just apply ground, 0 here. And then if it was storing VDD, it will discharge it down to ground. Remember that? So the direction of current was different. But did I have to flip the polarity of the bit line? No. Am I making sense? Okay. So I just have to change the level from VDD to ground. That's all. But here you need to flip. You need to either apply VDD here, 0 here, or 0 here, VDD here. So basically you need voltage for both of them. But you need voltage with opposite polarity. That's the difference. Did you catch it? There is a difference between DRAM and for DRAM, in one case you needed VDD, other case you didn't need anything, just ground. But here you need voltage for both cases, but with different polarity. So that's where the challenge comes. That's one of the biggest challenge of STT-MRAM, to have bidirectional write current. It's not easy to create. Okay. Are you with me so far? Okay. If so, we'll stop here today and we'll resume from this slide in the next class. Okay. Please review all of this before coming to class, because this is a new thing. It's not as easy as STEM or DRAM. All right. Thank you.